Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. All right, well, welcome everyone. Today we have with us Heather Miller, who I know from the Scala community. And Heather, you worked at EPFL, did your postdoc there, is that right?
PhD, I did my PhD there.
PhD, okay, cool. And so you've been doing, you've done a lot of Scala stuff, and now you're at CMU as a professor there.
Carnegie Mellon.
Yeah, Carnegie Mellon, thank you. Mm-hmm. And doing computer science stuff and doing some really fascinating research around distributed systems, which we will get into.
Mm-hmm. But and also a lot of interesting functional stuff. So
yeah, functional programming, composability.
Yes,
lots of great stuff. But welcome. Thanks for joining us, Heather.
Mm-hmm. Yeah, thanks for having me, and thanks for I think that I'm just randomly difficult to reach sometimes. I don't know. I've been sort of checked out on personal stuff. Just had a kid, so you were rather persistent in bugging me. So thank you, thank you for inviting me, and thank you for not giving up.
Yeah. Oh, of course. Well, we really did want to have you on to chat about all sorts of fun stuff. We had Jonas Bonaire on a while back and talked to. That was a really great conversation about distributed systems. But but want to get your whole take on that. But before we go there, what was your PhD? What did you study with EPFL in Scala?
Yeah, so my PhD was actually focusing on a lot of issues surrounding distribution and the Scala in general. How do we make this easier? Because it's generally just in some cases it just wasn't possible, just based on dumb little things that could be viewed as bugs, right? But the compiler emitted, references to things that would fail at serialization time, and therefore you couldn't distribute some object that you would, is totally innocuous. It's extends serializable or whatever. It looks fine, right? And so this is kind of.
And as soon as you try to pass it over the wire and use it, it doesn't work.
Yeah, and you just get runtime exceptions all over the place. And I mean, and this had to do with kind of how the Scala compiler encoded class instances and stuff like this, right? When when it got translated onto the JVM. So whatever, the point here is that this was just a bug that got fixed, right? But from this, there's a lot of issues that kind of popped up, and actually Matei Zaharia, when he was just a PhD student at Berkeley building Spark by himself quietly in an office, he was sending me emails all the time how does this, I can't, this doesn't work. Shouldn't this work? Right. And I'm you're right. That seems reasonable, Yeah. And then from there, there's a bunch of sort of questions that, became sort of the basis of my thesis. And some of them, so the whole idea of generating serialization code statically, and then, having some runtime support when needed, but generally to try to do it all statically. That was one of the first things that I did. And then after that,
you pickle.
That was the pickling library, and then there became 8,000 libraries.
Yeah.
Which there should be 8,000 libraries because there's so many subtly different ways to do things, right? And not every way is right.
Isn't it wild that it's 2021 and serialization of data is still such a hard problem?
Yeah.
Generally?
No. Absolutely.
It seems wild that here we are, 2021, and we're still struggling to get serialization.
But, gRPC, has been nice.
Protobufs. What's your take on protobufs?
They have largely prior to them, right? People were just serializing objects and sort of with some associated schema as JSON or something, right? As the format that you use to exchange between different objects between different programming languages or programs in general, right? And protobufs make it a lot more, I don't know, an encapsulated problem, protocol buff.
Right.
Protocol buffers handle the case of, how do I put my object into a certain shape that any other programming language can understand, right?
Yeah. So having an independent IDL gives us some benefits that we don't get if we're kind of doing the serialization on a language specific.
Yeah, exactly. And it also kind of having the IDL in the middle also kind of because let's just say that there's an object or a class or something that you want to take from Java into Python. There's all kinds of subtle differences in how fields can be declared and
different data
whatever.
models, different representations of
Yeah,
data.
but generally class, like the notion of a class is the same, but there's a whole bunch of differences, right? And so the sort of the common IDL makes it, like kind of smooths
Gives you
over those differences.
a shared model or something
Yeah,
that
right. It makes us like agree on something in between different sort of, universes of like modeling data. So
yeah,
I
and I guess
mean,
it's interesting that they built into that idea the appendability of fields,
yeah,
which is
the schema evolution aspect, right?
yeah,
right,
yeah, just recognizing that hey, schemas change, and we need to have support for that.
Did you happen to see? It's sometime in the last year or so. Brian Getz had a video where he was explaining how the security vulnerabilities of Java serialization.
Oh, I didn't see that video, but I've seen it. Okay, something in the last year. I've not seen that video, but I have seen a lot about this issue in general.
Oh, tell us.
Yeah, I mean, it's just like there's been so many like exploits and things, that are at their root some JVM like runtime serialization issue where you can kind of change and affect payloads based on like some runtime bug, right? I mean, I'm not going to pretend like I know exactly what his talk was about, but this general like issue is pretty. It's like, because everybody uses the JVM, right, as like in JVM serialization. Everybody has this problem who uses the JVM and uses JVM serialization, right? So you need to like update the whole virtual machine, and that's obviously not easy.
But I think the basic issue was that the fact that you could serialize behavior as well as data, and then you could spoof. You could replace a serialized method with your own thing, and
that method gets called.
Yeah, that's what he was talking about, and I was just kind of amazed that this has been in since Java 1. And we're only now, and it's like a severe, sounds like a pretty severe issue, and we're only now, because that's one of the benefits of records.
Right. Yeah, absolutely. And this is actually hilariously, so I'm not up to date on these things, so I'm going to give you like a snapshot from a few years ago. But when they were introducing lambdas into Java, they were like, let's not worry about serializing them, right? That seemed because and then this problem. However, this problem has been a problem since before that anyway, right?
Yeah.
Which I thought would,
Do we need to serialize anything other than data? Is that, I mean, maybe in distributed systems?
I think that's the point of records, is that you only serialize data, and it's just
and
nailed down.
protobufs, you only serialize data.
Right. And it's like, why would you want to send behavior over the wire?
That's us,
because, well, I mean, there's a lot of reasons why you might want to send behavior over the wire. People in the databases community have played with this idea for a long time because, you got a lot of data that you don't want to move. So why don't you just, and the functionality is stupid and small.
Instead of moving your data, move your behavior to the data. Instead of moving your data to the behavior, move your behavior to the data.
Exactly. Right. I mean,
interesting.
But if you do that, you have to really look at security and make sure
True, but I feel like live in a highly constrained like universe, and it's like all you have is like SQL or something, and you don't have like a general purpose language or whatever. Like there's a lot less to worry about. But I mean, there's still things to worry about. Like you could delete all the records, but people have played with this idea over the years, in multiple communities. I guess you could think of Spark as doing that, right? Because you leave all of the data on each of the machines in memory, and then all the code is compiled together, but ultimately you're like sending like, hey, invoke this create an instance of this class, invoke this function on the data that you have, on the data shard you have on your machine, right? And so that's you're not actually sending the function over the wire. You're sending a jar over the wire to all the different machines, right? And then they all have the same jars, but it's still kind of the same concept where rather than pumping all the data through one machine and just calculating the average, right, which is stupid, you calculate the average on remote machines, and then you aggregate it, and so it's kind of that, right? I mean, conceptually, it's that.
So your website said that you, like, your I don't know, research orientation is around rethinking how distributed systems work.
Yeah, that's like the most broad statement possible, I think. Like, I mean, like you were quoting me, so I'm not pointing at you saying this, and so I can say like we can zoom in and qualify that statement a little bit. So we do a bunch of things, and a lot of the focus of the work that we do is on composition. And so there's one area of work that we've been doing for a little while now. It's obviously since I'm a professor now, I work with PhD students, and it's really like their baby, and I'm kind of just like helping direct it along, right? But
keeping the money flowing.
Unfortunately, that's I think no, you talk to me about how academia works, and I will rant for like an hour and a half. But but like just talking. Let's focus on the research for now.
Yeah.
He's so you should know his name. His name is Matthew Wiedner. He's a PhD student at CMU, and he works in my research group, and he's been working on basically the problem of trying to ensure that nice guarantees that you want in a distributed context can compose, and that you can use these things that have these nice properties like you can in any sort of single machine program. So the example would be like CRDTs, right? If you want to use CRDTs, usually
what's CRDT?
Okay, I'll tell you what a CRDT is in a moment, but just for now, assume it's a data structure. Okay, it's a data structure with some distributed systems niceties.
Okay.
And the current state of the art is that well, I have to use an implementation of one of these things out of a database, and I can't really do anything like with it, right? I can't like create like a new class definition that also has nice distributed systems properties and has like other CRDTs, which are data structures, like as fields, and then expect all of those properties to compose nicely in whatever I actually instantiate and play with, right? So I don't know if that makes sense, but the point here is that you can't use them like regular data structures. They have these, so the properties that I'm talking about are like eventual consistency. So we want, if we have replicas of this data structure on different machines, and we want to just use it like it's any other data structure, the way that you construct them and you put the pieces together, you can't do it the same way that you can when you like create like your own data structure and you use other data structures as fields and things. It sort of everything breaks down when you start trying to like build up a composite object that has like these nice distributed systems properties.
It's like the systems aren't aware of the concept of eventual consistency, and so you can't compose them when you're running on a single machine. You don't even have to worry about
it's always consistent.
It's always consistent.
Yeah, exactly.
But yeah, as soon as you go into the distributed space, there is the reality of eventual consistency, but that is not expressed through the programming model in any way.
Right, exactly. And so like let's just say, so here's a stupid example, right? Like since the world's easiest like eventually consistent data structure is like a counter. Let's say that we're building a web app, and we want it's a collaborative web app, and we want all three of us have a laptop or a smartphone or something, and we want to be able to like upvote the counter and all see the same result. So like James can update the counter twice, and Bruce once, and me once, right? And then we should all see 4, right? And the way that people would implement that, like right now, like let's say that, okay, here, you guys have the task of doing this. You tend to focus a lot like on RPC calls and like, how do I connect to these things? And then like, how do I ensure that we all have
centralize it into a single database, a single node, a single, if all of us are, and then use locks on that database, and all that.
But you're focusing on all these aspects of it, really, and that's okay, fine. I'm glad that you know about those things. Congratulations. It's a rather common pattern, and why do you have to go through all that crap and also do it wrong in some cases because maybe things about distributed systems, but like however you decide to lock things is bad, right? And it slows everything down, right? Like
so
you don't want that.
Like let's say you go distributed, one of your options is to then have a centralized coordinator,
right, and then have everything locking through that.
That's right.
Which is, basically your centralized coordinator is fundamentally serializing everything, and you don't need to do that because it's just plus ones. You can always just aggregate them in any order that they come in, right? Like it's not required to have somebody like force a serialization order, right?
Yeah.
Anyway,
So
but
CRDTs, how do we do it?
Yeah, so CRDTs. So basically, CRDTs. They are not a concept that I invented or anything. They're something that have been around for a little while since 2011.
And it's an acronym for what?
Conflict-free replicated data types.
CRDT.
CRDT.
Conflict-free. Just
where's the F?
Ignore the F.
Oh,
yeah.
Okay.
Yeah. Sorry. Yeah, conflict-free is one word. Just imagine replicated data type.
Okay.
I didn't name them. Don't blame me either.
Okay. No, just trying to be clear.
Yeah. I mean, we can all just call them replicated data types. But the point is that by design, you should be able to have basically these things should be able to be replicable. Replicable, I don't know, whatever that word is. You should be able to replicate these things, and everybody who's using them and updating them, you update your replica locally, and then when your updates will eventually be merged on other people's replicas. So in the counter scenario, I have a counter, James has a counter, Bruce has a counter, and you all everybody just kind of clicks one, like +1 whenever you feel like it, and then my updates will eventually get to yours and then be merged, and they all kind of come in whenever they come in and get merged, and then we all eventually see the same state. This is obviously easy for a counter, but there are other situations that are not easy.
It's easy for a counter because it's commutative or something.
Yes, exactly. It's commutative, right? But then not everything is only commutative. So think about adding division and like subtraction and stuff to it, right? So if you have like an order of operations for like a little, like computing an average, for example, right? And so things have to happen in a certain order. And sort of the TLDR of a recent paper that we had published at ICFP, which is the International Conference on Functional Programming. It's this notion of, I'm not going to use all the terminology from the paper because it's mathy. I'm just going to give like a gist of it. The point is that you can define a so-called like arbitration order. So like rules for what to apply first. So in the case of like subtraction and multiplication and you can kind of like specify an order of operations, and each of the individual replicas will know what this arbitration order is. So if an update, if you get like a subtraction operation before like an addition one or whatever, like it should know how to reorder them in the right order so that you get the correct result. And so this is
similar to another CRDT. So you mentioned like the counter example, but then there's another CRDT which is something where it knows the directionality of states that it can go through. So so Akka uses this for cluster state. So a node can't go from starting to down. It can only go from starting to started or something like that.
Yeah,
like it knows the order
down
in which
down.
Yeah, and so because the CRDT defines this order that things can happen in, it, as the resolution is happening, it knows which events it can discard or whatever, because it knows that they came out of order or what may have come out of order, and so then it knows what it can discard.
So in our case, we don't discard. We just because we know that there must be like
reassemble into the right order or something.
Yeah, we know that we're waiting for something, and so then when it arrives, then we'll reassemble everything and then do the computation.
Cool.
But the point is that this is like a general like this. So in the case of like Akka's like cluster status situation, that's one application of it. The other application is just like regular order of operations and multiplication and subtraction and division and whatever. But like the point is that you can kind of have this sort of arbitration order for like a lot of different applications. It's not like and this is and you would typically, when you create your data structure, you'd want to kind of specify what this is, because ideally what it should be, and the person who is like downstream just using your data structure knows that something smart's supposed to happen, but they shouldn't have to like implement that themselves, right? And so the key idea here is basically encoding this so-called arbitration order. The paper is about it's about semi-direct products and composing operations and whatever. It's like a bunch of jargon. And I mean, if you like functional programming papers, absolutely by all means go read it. But I just want to be clear that this is not something that like, if you're into functional programming and you're like writing web apps and you've taken some tutorials, this is not going to be accessible at all, I promise. So to be clear,
is so cool about this is that one of the things I love about functional programming is that there is this whole mathematical foundation to it that makes it work.
Yes.
And like monads, like very mathematical foundation to it, but we don't have to understand the math
not at all
in order to get use out of monads, but we certainly benefit that monads are based on algebraic foundation.
It's reassuring.
Right. Like you go,
you don't have to know it. Like
yeah, but then it makes it the explaining of it is challenging because so many people come from the math background and they want to explain it mathematically. And it's going to lose everybody.
I don't want to explain the math background. I want to explain the application, right? And I want to be like, hey, there is a math background. Don't worry about it. If you really want to worry about it, go read the paper. It's a mathy paper, you know.
But I think that
you don't need to know that stuff.
This is what's super cool that you're doing is that you're creating these defining and creating these mathematical foundations for distributed systems.
Mm-hmm.
And so that now, whether it's CRDTs or other things we discover, they will be based on math and give us reliable ways to compose.
Put things together.
Yeah.
So let me back off a little because of what you were talking about. I was thinking, well, like the counter. If we were all sitting at the same computer and pushing the counter button,
this wouldn't be a problem.
Oh, it happens. Just do it right now.
Yeah.
But then when we're separated, it becomes a stream of events.
Exactly. Stream of events that have to be submitted over the wire, and they could come, at any time, and yeah.
And
so,
it also seems like you can, using math, you can say, oh, we can figure out things about these events, like maybe some of them we can ignore.
For example,
some CRDT, with some data structure.
Yeah. Okay.
Right. So that's the case of the Akka kind of cluster status CRDT, I guess that James was talking about, which is, we know that you can't get to state, from state A to state D without going through BC, right? And so we can like assume we got through BC and we jump over to D, right?
Or wait until you get the thing that.
And so in our case, we wait.
And so this kind of a math analysis of it could allow you to compose distributed components.
Well, exactly. So the idea is, if I can encode like how these things should be combined, right, into like the data definition or in sort of like the implementation of the CRDT, I should be able to just pick that thing up and use it with some, I should be able to use these like this data structure with some other data structure, and together I can figure out the correct arbitration of messages. So I can use these things as fields, and then not have to worry about all of the guarantees are now invalid because I've put these things together somehow, or I've added a new operation or something to it, and therefore I have to redesign this thing from scratch and improve all the properties about it again. You don't have to do that with this. So I guess the point is like, I like wave my hands like math, but that math means that like you can use this distributed data structure in the same way that you use not distributed data structures. And you can just have like a library of these data structures. The weird part about it is that there's like some networking code that has to exist in order to send messages places. So that's what makes the library awkward. But other than that, like the way that you use it, you can just like add functions to it, right? And it has this arbitration order. And so you don't have to like rediscover all of the ways that things can be combined and how they could go wrong, because this mathy arbitration order thing underlies it all. And you kind of like always fall back to that. So I don't know if that makes sense. Like I'm trying to like give an intuitive description of this and like why it matters. Obviously,
and ultimately it's so that we
can mathematical details.
Yeah, ultimately it's so that we can compose distributed pieces together, and in a reliable way, right?
That's because that's the kind of the way I'm coming at functional programming. This idea of composition seems to be front and center to me. It's like, that's why we're doing all this, so we can take these little reliable pieces and compose them together into big reliable pieces.
Right. Yep.
And you're trying to do that for distributed systems. You're trying to apply
for
that.
properties for I guess you could say for properties of distributed systems. I mean, ultimately, I don't want to claim that like the things that we're doing, it's like we're like making zookeepers that are composable or something. Like that's like 18,000 levels higher than we're working. We're working on like the data structures, and we're for example,
have to get the foundations there, and then we can build abstractions on top of those that are a better
the foundations and how to put them together.
Right. And so we're focusing right now on the data and ways to compose the functions on the data, right? We already, so this sounds all weird and abstract, but the ways in which it's like actually like usable and kind of cool right this minute is that it lets you build like collaborative web applications with just like a library of data structures. So it's like, here, I'm gonna get like a register or something, I'm gonna make something out of this, right? We have a bunch of, so one thing that's cool about working at a university is that there's a bunch of students around, and so that it's a good like, this person knows a reasonable amount of things. Like, she's a senior in computer science, she's worked at a whole bunch of companies for internships, she like knows what she's doing, but she's terrified of like building collaborative web applications. Would it be hard for her to build a collaborative web application in like a couple of days, just like using these distributed data structures like you pluck out of a library like any other collections library? And I mean, we have a bunch of applications that we built that are like, would typically be very difficult, like collaborative like whiteboard drawing applications, or like of course the to-do list thing, but the text editors and all kinds of stuff that we've built just like in a day or two, that have all of these properties that are really nice, and you don't get into weird inconsistent states at all. And you just have like undergrads doing it because it's just like, I'm going to take like this collaborative data structure out of this library and use it, and then put it into my front end, right? And that way you focus on that. You focus on the data when you're writing the code, and you don't focus on like all the damn RPC calls and having to manage the state and all that crap, or having to build your own centralized server or something. You just get the data structure out of the library and you use it, and that's it. I mean, you have to have, like I said, there's this networking layer, so you have to have some way to get messages between your clients. But you can just stand up a little Heroku instance, right? and things can go through that Heroku instance as like sort of as a beginner case, right? And you can actually Matthew. So this is Matthew's work, right? Matthew has also been doing this like completely decentralized without the need for a centralized server. And so he's been building like collaborative applications and like putting them on this Matrix, like the Matrix chat application thingy that's fully decentralized, whatever. He's been putting like applications on that. And so by that, by doing that, like the little collaborative applications that he's building are also completely decentralized, where there's no centralized server. Wow. And so, and the point is that it's like a couple, it's just like some data structures that you pluck out of a library and use, and it's collaborative. He actually gave a talk at Strange Loop about it a couple weeks ago.
Oh, cool. I'll have to check that one out.
Yeah. So I was, so the talk is billed for him and I, but I could not travel. I was hoping to go, but the baby was a little too needy, so he ended up giving the talk. But it says my name on there with him, because we did it. We were, obviously this is joint work, right? But if you look up my name on Strange Loop, you'll find Matthew's talk, which is who you should be listening to.
So I have a slight change in direction. I think in terms of failure, like. Well, like, what do you think about the Erlang Elixir approach of saying, if a piece fails, just put it back up, and also sort of the Byzantine generals issue and how you're dealing with that? When we think of, we've been studying,
Scalazio.
Scalazio stuff and everything, and it's like failure. Okay, it's an effect. We have to deal with it. How is your research?
So. That's a good question. That specific project is not considering failure, mostly because we're talking about kind of like right now we're doing like these little, like we're doing like text editor apps and things like this where, A, failure typically doesn't happen, and B, like if failure does happen, it's just like a client goes offline for like 10 minutes, and then comes back online. That's failure. It's not really failure because it comes back. So we're not really considering failure in that case. However, there's a whole bunch of other research where I guess it's a different kind of failure. It's we're dealing with like failures in much larger systems, and then trying to identify those before they get into production, so that at least you can debug it before it brings down, an entire, I don't know, Spotify or something like this, right? So
I guess there's a difference in use cases between a collaborative system and like a transactional system,
right?
Not being the only two types of systems that you could build, but transactional, where it's like, oh, I just hit checkout, like that has a very different. You have to approach failure to that very differently than you would in a collaborative type scenario,
right? And so to kind of like pivot over into that stuff. So this is Chris Micklejohn's work. So everybody knows Chris, I hope.
I don't know Chris.
You don't know Chris? Oh, he's like, everybody knows Chris. How do you not know Chris?
Maybe I do.
Chris.
This is a distributed network issue, right. I think.
Yeah.
Yeah.
So Chris was one of the engineers at Basho back in the day, and he worked on CRDTs back then. Cool. He's now a PhD student at CMU, and he actually started out like doing like a programming language or programming models and stuff like this for CRDTs is like what he wanted to do. But he since then has pivoted into like, trying to deal with the issue of failure and identifying, failures in distributed systems that are like completely just, bugs between teams, like not like, Zookeeper has a bug, but like I implemented a microservice and it did not like consider, this other guy's service being down. Right. And then, through some cascade of bullcrap, like the whole service, like everything came down. Right.
Cascading failure.
Yeah. Right. And so this is sort of his whole thing. And how do I get into like the basics of it without like going down a rabbit hole and boring you to death?
No, let's go down the rabbit hole if you want.
Struggle a lot with failure.
Yeah.
Yeah. So okay. This is kind of in the realm of chaos engineering, but without having to do chaos engineering, because if you think about doing chaos engineering is rather expensive because it means that you have to stand up a whole like replica of all of your services, and then you have to have a team of people like, in a calculated way shutting things down and then observing what happens and then trying to like backtrack like what should have happened and which team is responsible, right? It's kind of like what people do in
the mathy way to do it.
Yeah, that's it. That would be
so we do have some
actual throwing things against the wall way of doing it.
So I'm not going to claim that this is like, has like beautiful foundations in the way that like functional programming stuff does, but there is a nicer foundation to it, I think. And the idea is basically like, we look at services as like individual things that are like black boxes, and we kind of know what their interfaces are. And we usually they're always communicating, with protocol buffers over gRPC or HTTP, right? And if you just look at, the possible responses that you could get from either of these, it's a finite space of possible responses. And all of the things that all the requests that a service can make, and, all of the possible responses that it could get. And, you kind of build this graph. You can dynamically build this graph, like the service graph, to figure out like what are all the services. And you can kind of, build this giant state space of potential possibilities that your system can get into. But what Chris has done is he's kind of figured out a clever way to prune the space down. And it turns out that there's actually not like a huge, like it's not an intractably large space of things that could go wrong.
So if you take like service topology and all the like possible states of across a service topology, it seems like the graph just explodes exponentially at some point, and you can't reason about the graph anymore. That's what it would seem like. But you can.
But you can because because we focus like on sort of like the interfaces between these things and on ultimately the responses that you get, like the HTTP responses that you get, right? And so and then usually since we've built the graph, we can trace back to exactly which service triggered all of these things. But it means that we like it's like the number of services and the number of requests that they can make, and the possible space of different like HTTP response codes, right? Which is, you put all these things together, it's not that huge. And then in addition to that, you can prune a whole bunch of these out, because several like if you just kind of exhaustively generated all the possibilities, like I don't know, okay, depending on the topology, it can be like most of the things that you've generated are kind of the same case, kind of repeated, but with just two little things out of order, right? But they're ultimately the same, so they kind of project down to the same scenario. I don't know if that makes sense, but that means you could prune it out, so then you'd end up with a lot fewer, like potential messages that you might be receiving and handling. I don't know if that makes sense, but the point here is that like we can prune down this ginormous space of like, here are all the things that could possibly go wrong. But we generate all these things that could possibly go wrong. We throw away a lot of them because they project down to the same sort of trace. And then we end up with usually this set of not very many traces, and we can run that through the entire code, or that through the actual implementation code, and then see what the implementation does. And we do this as CI. So you don't have to do it with like a bunch of engineers, like in a big data center or whatever.
Right.
You can just run it through the individual services.
Me think of the distinction between pure functions and effectful functions. You say pure functions, we know how they work. The effectful functions are the ones we'll focus on.
Isolate, put the
isolation, right.
The mental image that I have is that if you have like a 3D structure that you can hold, if you hold that up and cast a light on it, you get a shadow of the structure, and essentially that's what you're doing is you've got this like very complex topology, but when you then project that into a 2D surface, you're able to collapse a bunch of stuff down.
Mm-hmm. That's the right way to think about it. And like in this case, stuff would be like the potential like calls in like a graph of RPC calls or something, right? So it's like call A and call B could happen in any order, but the end result is still the same, right? And so therefore we don't have to try both of those scenarios. We can just try one of them, because we can prove that they're the same thing.
Yeah.
And so that's...
So Chris's project captures this like projected topology, and then can test at CI time that what's going to happen in the different scenarios, and see where cascading failure may happen, and tell you about it in CI.
Tell you about it in CI. Exactly. And you can identify like which service might be causing it and which team is responsible for it. It doesn't. So to be clear and totally fair, like I don't want to say that this is a complete replacement for chaos engineering, but what we did was we went through a bunch of chaos engineering talks, and we've like recreated the issues that happened, and majority of them we can catch with this approach, but there are some which you can only catch with chaos engineering. So the point here is like, this could be a much cheaper first step, right? And then you catch a bunch of bugs this way, and then you go for chaos engineering to catch some of the more like Heisenberg issues or whatever that you might be looking for. But the point is that like it could save a whole bunch of money and time, because we can all afford CI time. CI time is cheaper than engineering time.
Well, and in chaos engineering, we're typically actually causing service disruptions intentionally, whereas if we can take a lot of that and put it into CI so that we don't have to actually cause service disruptions to find these issues, that's a good thing for our users.
Exactly. So and that, I mean, that's the idea. You don't have, because some companies, the way that they do it, I guess, is that they have kind of like a canary deployment or whatever, that they're doing all of a sudden. They have some small number of users using it, and then they cause an outage or whatever, and they just kind of like redirect everybody back to the the bigger deployment, right? Like, oh crap, now we have to figure it out.
But some users have to suffer. It's like we're gonna let some users have a terrible experience while we use them as the guinea pigs.
As our guinea pigs, exactly. Yeah. But then in addition to that,
if we didn't have to have actual users be guinea pigs.
You got a whole bunch of machines doing stuff that they don't need to do, right? Like you've kind of doubled the size of your anyway. Like this seems just very expensive if you can catch a lot of it at CI time.
And they could be mining Bitcoin instead.
Yeah, that's hard to detect, I have to say. But the cool thing is that Chris is actually doing this. I'm not allowed to say with who, but with one of these big trendy tech companies that has a lot of microservices.
Nice.
And this company is finding it very useful. Yeah. So like he's testing it out on their services, and they're like, yeah, this seems good,
That's cool.
But he's tried it in small scenarios, like in a handful of services. He's not tried it like on 10,000 services or something.
Yeah.
But it's like it's not he's trying it on real things. It's not like just on some dummy, like we invented some stupid scenario and we're going to claim that it works for everything because we're academics. It's not like that. He's doing it at a real company that's one of the trendy ones.
That's cool. Yeah. And with so many of these problems, it seems like going back to kind of where we started with serialization, it's a problem like build tools, where you look at it on the surface and you're like, this is a simple problem.
I can fix this in a weekend.
That's right, exactly. And then you realize just how complex the space is.
How much crap no. And then also like and once you get into the middle of it, you're like, I got something that mostly works. Then you start discovering like all of the shortcuts and like ugly stuff that the other frameworks and other things are doing, like the way that they're like fudging things, and you're just like, damn, this is messy. And so
it does seem like sometimes if you change your perspective or orientation, or you move into a different solution space, you apply a Laplace transform on it or something, then the problem drops out.
Yeah.
It's often
if you take a completely different approach. That's right. I mean, and I like to doubt what research is for. I mean, in some cases, research is like, just speed this thing up using the same 7 techniques that we've been using, but in differing amounts, like sometimes that's research. But, I like to think of research as like kind of turning the problem sideways and then trying some totally out of left field approach. And maybe it's going to work, or maybe it's just going to be weird and wonky, but, we've successfully made it work a few times. And then we have kind of a new way of doing things, whether it's good or bad. And that's the one thing that's still cool about research. All of the drama with funding is not cool about research. That is very uncool.
Yeah, well, and it's cool that your research at UPFL around Scala serialization stuff really, I think, opened a lot of doorways to doing the serialization, constructing the serialization stuff pre-runtime. And where I've been experiencing this a lot lately is with GraalVM native image, and we talked about that on our last episode. But with GraalVM native image, it does ahead of time compilation. I don't know if you're familiar with it, but it does ahead of time compilation of JVM based applications, and that is not reflection friendly because reflection is dynamic, so it can't be ahead of time compiled. And so it's been interesting to see the existing serialization libraries all kind of really struggle through dealing with this because they're based on reflection. Even ones that have very little reflection usually have reflection somewhere. And so then it becomes tricky and difficult. And so in working in the Scala world, where a lot of the JSON libraries now, or serialization libraries now, don't use reflection at all, they use macros.
Why?
I'm like,
if you use ADTs, why? We don't need reflection, right? Because we don't, as long as you don't have an ugly object graph, you're good. Ugly object graphs are the problem. That's why you need reflection, because anybody can mutate this thing in any way. But if you're doing functional programming and you have kind of like a tree-like data structure that's not going to change, generate ahead of time. Who cares? It's going to be way better. And also, like, it's going to be predictable and faster at runtime. Yeah.
Exactly.
I did this back in, I don't know, 2012 or something. And then obviously, like, this doesn't work and this should be faster and this sucks. And like, then people make their own. I'm like, great, I'm happy that that you found a better way. But
no, I think your work definitely, the research that you did and the work you did put us into a much better direction and allowed the community to be like, okay, no, this is a better way and we can make this work.
And it's actually really interesting because like a lot of the flack that when the serialization library didn't work, it was because it had to fall back to reflection, and it was using Scala reflection, which is terrible. I mean, it had. Let's just say it was terrible back in the day. It was terrible only because so Martin would always be like, don't use reflection, da 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 da, you know, it's whatever. But the point is that back then it was made like basically the reflection, like Scholar reflection was basically like just exposing all the compiler internals. And if you are fixing bugs in a compiler, that's terrible, because if you change something subtle in the code, which causes like, I don't know, the class files to be, you know, or the you know, the source files to be compiled in a slightly different order or something, it means that something isn't yet compiled that you were like using the API to, and then now you're going to get like nothing's going to work. It's all going to break, and you're going to get just explosions of terrible, ugly. And that happened a lot with the first serialization library. It was because you know, there would be a compiler fix that would just cause everything else to break, and then it would, you know, ultimately be the serialization library's fault because it spits out all this ugly, you can't figure it out. But this is also kind of one of the things, like, you know, one of the ways that we realized that the approach to exposing all these compiler internals via like a reflection API is a bad decision. And then if you notice, like, that has been removed. That's no longer, that no longer exists, right? But there are a lot of libraries that, you know, and this is, I don't know if you remember Macro Paradise and all of that. You know, people who built libraries on top of that, you know, would start trying to reduce the area, like using reflection, you know, and the fancy stuff, because little compiler fixes that, like, you know, Jason Saug or Seth or somebody would do that have nothing to do with something else would cause this cascading issue. And then, you know, it would come out in some innocuous, some library, right, that had nothing, that has no idea anything about the compiler internals.
An extreme example of coupling.
Yes. But,
true.
But this is part of the reason why so many serialization libraries popped up after. So you know, because I was like, ta-da, we had this really cool approach, and it, you know, it worked for all of the things that we made it work for. But then, you know, some compiler bug would be fixed or something, and then, you know, something that worked and that's like advertised to work would then appear not to work anymore. And people are like, I can do this on the weekend, you know. I can do something less shitty that works on the weekend, and then they would do it, and then now you have 20 of these libraries, and I'm just like, I don't know what to do here.
Well, now with Scala 3, I think we're starting to see how people are using, not going to macros for these solutions, but using the derivative type classes to solve these problems, and then that creates a much better isolation layer. But that, would you want to explain G80Ts to me?
This like I've never been able to explain them clearly ever. So I mean, I would
understand them at all, but
I feel like I understand them, but I can't articulate them to somebody else well enough.
The curse of the GADE.
Curse of the monad, but I mean, it's one of those things where it's like they're so hard to explain, and then you start trying to explain it, and then you like talk for 10 minutes, and then nobody understood what the hell you just said. You know what I mean? And so I feel like, so I'm going to say no.
I guess that's good.
Because I have not mastered this explanation.
I guess the TLDR is that there is a mathematical construct behind type class derivation, which gives us a better way to do metaprogramming.
Or what feels like metaprogramming, I guess, you know, like something at compile time. Like, because that you know, that's the similarity here, is that all the type class derivation stuff is manipulation that you are doing at compile time, and, you know, macros are manipulation that you're doing at compile time, but it's like manipulating like the actual compiler code, right, versus you know, doing something nice with abstractions in the case of the type level stuff.
And ultimately back to the serialization is that this is getting us to a place where we don't have to use reflection. We can instead do full compile time serializers and so it's cool stuff.
and the stuff that I did was based on macros, you know, and this is, you know, widely accepted to be not the right way to do these things nowadays.
And I mean, if you were starting today, you would probably be using Scala 3 type class derivation.
Yeah, for sure. But I'm just saying, like, even Scala 2, like, you know, it's been accepted for a long time now that probably don't do it that way. Mostly because of the fact that you have this window into the compiler, and that stuff is all changing, and you have no idea what's going to change.
Yes. I think Josh Surratt had taken some of your pickling stuff and done protobuf support on top of it, from remembering.
Oh, probably. I know he was messing with it at one point.
Yeah.
I mean, you can kind of create your own IDL for it. And I mean, by create your own, you can just, create a protobuf,
Yeah.
IDL, right? That was another sort of thing, was trying to make sure that it would remain extensible.
Right. Yeah,
so that you're not locked
different,
into
different serialization formats. You could do JSON, you could do, and then I think Josh added
the
protobuf, and I don't know if you did XML or whatever.
We always said that one could do XML, but then nobody actually did.
Right.
I mean, we showed you how to do JSON and we showed you how to do binary, and then we're like, okay, and one could do XML because I don't want to continue to encourage XML.
Yeah. Yes.
I remember and then XML was the new hotness.
It was the new hotness.
It was going to be everything.
Yeah, everything. Solve all the problems. One of the things I was thinking about with serialization, to dwell on that a little longer, was, and one of the challenging problems to it is that I think oftentimes when we look at serialization, we're just thinking about one problem space. So maybe we need to optimize for over the wire, like not taking a lot of space over the wire or something like that. Or maybe we need to optimize for deserialization efficiency, or maybe we need to optimize for being able to be compatible across multiple different platforms and languages or whatever.
Conversions.
Yeah. Or maybe we need to optimize for maintaining a really rich representation of the data or something like that. And so it's one of those things where it's like, usually when we think about serialization, I just think about, here's my problem that I'm trying to solve with serialization, but we don't think about how the problem space is actually gigantic.
Huge. And also everybody comes in out of like left and right field with completely different needs and concerns, right? So we actually, so this is something that I think people don't remember, don't realize about the whole serialization stuff that we did back in the day. It was intended to be flexible. Like, it was intended to let you, like, if you wanted to override it and, like focus on only like a compact representation because you wanted it to be, you wanted to reduce network overhead, right? But you didn't care about CPU. So like, it could take a long time to reconstruct the object if you want, but like, as long as it's as compact as possible. We gave you, so, I used to ramble, oh, it's extensible, blah, 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 blah. But this is what I meant when I was saying that stuff. And so we let you control both the representation and then how the representation is constructed. Yeah. And we kind of gave you like an API for how we like represented objects. And, you could override the way that we did it. So we had a binary serialization like thing where we would, take the schema or whatever, and we had our own way of encoding it in binary. And like, these two things were like separate extensible APIs. So you could change the representation, or you could change like how you convert the fields and things like this into that format. And so, we basically just compared and contrasted JSON versus like this binary format, where the binary format, the goal was to be as fast and compact, as we were like jointly optimizing those two things. And then obviously for JSON,
one API that allows you to achieve whatever your needs are around serialization. I'm sure that was
extremely ridiculously hard. And I think, like nobody like thought about that. I kept them being like, it's extensible. And everyone's like, yeah. But it's at runtime. It's generated at compile time. It's so fast, and I'm like, yeah, that too, But that was
like throw your own types into it. Which is another hard problem of serialization, is like, okay, what do you do about the types that are not the primitive types, that are user defined types, and how do you
how do you
code those and decode those? And
but this is I guess, like, if I have like a style for doing things, it's like taking the PL stuff to the system stuff, like using like doing PL things to, because in PL land we like generality and reusability and extensibility, and it's like, we like these things, we value them, but in systems land it's just like, how do we do as little work as possible? So we're going to build a specialized system to only do binary whatever from Python to something else, and we will make it the fastest, right? And so I'm like, no, let's have all of those things, but into one system that's flexible and blah 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 blah.
Yeah.
And so, and I mean, you could say that that's exactly kind of the same style of like how we're doing the composability work, right? We're like, let's use the nice PL composition stuff, but like compose the systems properties that usually you build a brand new system for each time. Let's not build a brand new system. Let's just make these things composable so you can put little pieces together and have a new system, like without building it all from scratch.
I guess functional programming has given me a perspective on this that now I'm annoyed by systems that don't value composability as like a first class, key thing.
Like, or just like being able to reuse things and extend them slightly or whatever.
Like Kubernetes. I mean, there's a lot of great things about Kubernetes, but the fact that there is like no composability model, like just like hurts me in my soul. Like, like I really want like to be able to like compose these CRDTs together, like, and the fact that isn't part of the design, I think is just fundamentally wrong. But I'm thankful that there are people like you that are doing research into how do we bring that composability, the PL design stuff to things larger than just languages, to systems and distributed systems. And
so it's really, I have to say it's really an uphill battle where like we submit our papers to systems conferences and people are like, what the hell? Generality is a dirty word because it means slow, right? And so there's really still, I mean, I'm trying, the people in my researcher group are trying, there's a couple people out there trying to do this stuff and like make things, whatever. I'm just going to use the word composable as a blanket term for all the stuff that we're talking about. But there's really like a clash of different cultures. So the people who are building systems, I mean, it doesn't have to be academic people. It's, people who are building systems in the real world, right? Like both of those groups of people are very allergic to this notion of like generality and flexibility and blah, 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 because that's typically seen as, something that's going to distract from the bottom line. And, it's not going to be the specialized fast thing that we wanted.
And I'm like, why do you hate math so much? It's so good.
There's a culture clash. And and so so it's funny because me and Chris have had it. So this paper describing this fault injection stuff that's, like, don't do chaos engineering all the time. Do this stuff and then do chaos engineering. This paper, he just presented it like 2 weeks ago at the Symposium on Cloud Computing, so SOCC. So there's a paper, it's available, blah, 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 blah. If anybody wants to look at this stuff, that's accessible. I would say read that paper because you can read that paper.
Oh, cool.
The math papers are hard to read, so don't read the math papers. But, like that paper took probably, I don't know, like we submitted it like 3 or 4 times. And before it finally got in anywhere, because of this like culture clash, right? Where we would use words like, composable or like general, and then that would immediately trigger everybody to be like, this is impractical. It's like, but we're doing it on some company's thing. Like it's not impractical,
The shift to functional programming is a fundamental mental sea change.
Yeah.
It certainly is.
Yeah,
it certainly is. I will not argue that, but it's just, there's this other problem, right? Which is the cultural problem, right? Like there is this mental change that nobody wants to undertake. How do you show them because right now I'm just dealing with the knee jerks. Like we haven't even been able to like show an example all the way through to people that are like, oh, this isn't so bad. It's just like, oh my God, generality. No,
Well, and sometimes it takes those higher level abstractions being built on that foundation for people to understand, to be able to relate to it. Because like I totally love the concept of CRDTs, but I don't personally want to build stuff directly like with CRDTs. I want to build stuff that is built on top of CRDTs.
Right.
But
you don't want to deal with them.
As a mediocre developer, CRDTs are too hardcore for me,
But you don't. But the point is, you should not have to understand a damn thing about them.
Right.
Is kind of like our argument. They do all kinds of hard crap under the hood. Like, can we just keep that hard crap away from you so that you can just like reason about putting them together?
But have
like
that
Lego
solid
bricks?
foundation there.
Yeah.
And the algebraically.
Well, yeah, that functional programming principle of, okay, we're going to do the hard stuff once, and then you're just going to use this tool.
Yeah, exactly.
And know that it's going to work and it's going to compose.
Right. Mm-hmm. I wish that like this could be seen by many people who build some of the systems that we that we use, because it's there's not enough of this like willingness to accept these different foundations.
Yeah. Well, and I guess one of the things that functional programming has done to me is it's made me really significantly value having this foundation, whereas before functional programming I was unaware of why I would need that foundation and what value it would bring me.
Years ago I saw something about people who were going to try and make programs provably correct using math, and I just thought, well, that's ridiculous. That's impossible. Why would you even try and do that? And it's taken a long time for me to go, oh, I see how. See how that's at least partially possible,
and partially valuable, and
super valuable.
Super valuable.
Oh yeah.
But everything starts out that way, where you're like, "That's crazy,"
Yeah.
And internet
like,
that's on all the time in your house, nah,
crazy. Yeah. Okay, well, Heather, thank you so much for sharing your wisdom and knowledge and experience with us. Super fun to learn from you, and hopefully I get to see you in person sometime at a conference.
Oh yeah, that would be nice. It's like I don't remember conferences anymore. It's like it's so bad for Matthew, who is the guy working on the CRDT stuff, is like awesome and delightful, and he's appeared to do his PhD and did all of this work like during this pandemic. This poor guy has like done all this stuff, and he's like, he went to Strange Loop, which was like, and he presented at Strange Loop last talk of the day at a very slimmed down Strange Loop. You know what I mean? And I'm just like, I swear it's better than this, man. I swear it's better than this.
Right.
So it's like, I feel bad for them, right? Because they're just coming up and they
haven't been able to experience.
They haven't been able to meet anybody or do any of the excitement that you have when you sit down with some people and like
sit in a hotel lobby till 2 a.m. talking about CRDTs and
or like working through something on the back of a notepad or whatever. Yeah, like he hasn't had to experience those things, and I look forward to experiencing those things again. But I want him to. I want those folks that are just coming up to experience those things, because this pandemic has been going on long enough, man.
Yeah.
I want it to be over.
Oh, yes, we all do. Well, thank you so much, Heather.
Yeah, thanks for having me. I appreciate it.